Okay, I think we're recording. We'll go through your questions in a second. I just did a quick kind of review through some of the specs quizzes, and perhaps comes as no surprise. One of the I would argue two of the standouts have to do with structure. So in particular, we get the bond line structure. That one always kind of trips people up because you're trying to convert from a formula process out to a structure. And that will always be a challenge that's just going to take time to kind of get used to. I would recommend practice with that. Um, it is going to become super critical, as you'll quickly see, because we then want to be able to interpret those structures beyond just the art class. So those first few specs quizzes are effectively just art class. How do we draw these things so that we're all on the same page with what we're representing? Resonance is now one of those interpretations, and it is going to become a challenge to navigate. I was hoping to get a little bit more time to try and, creatively come up with a structure. And I don't think I'm going to be able to manage being all that creative, but we will take a look at an option with this. Bond angle's a little gross. Try and clean that up. That now looks like a double bond. It is not a double bond. That's double bond. So let's take a look at this structure. What I'm going to have you do at your tables is first take a minute and try and come up with some resonance structures, and then share them around at your table. If you're identifying that you have different structures, try and come up with explanations for why one structure is better than the other. I did intentionally leave some stuff off here. If we're going to consider how many resonance structures, 1, 2, 3, 4, 5, 6. I think I can come up with 6. And I could easily be screwing something up within that. But I think I've got 6. So it's going to suck for the recording because now it's going to be quiet time where everybody gets to try and figure out your possible resonance structures. And I'll come around and bother you. Okay, so let's talk through that. Okay, so how many electrons do you have around that nitrogen? Okay, and so what you're doing is falling into what I would argue is a 151 shit show trap. Okay, every one of those lines represents 2 electrons. How many electrons are around that nitrogen? 2, 4, 6, 8, 10. Can nitrogen have 10 electrons? No. Okay, next part within this, which is kind of a different tier because it's going to come to how you're coming to your resonance structures. I would argue you should come to your resonance structures by finding electrons and moving them and showing how you're going to move them. That's our curved arrows. What I see right there is you have a structure and then you have another structure. I have no idea how or why you connected to get those systems.
I think it makes sense. The only thing you can do is either move it to the atom or the next bond, right? Well, really, you can move it from atom and then atom to there.
To bond?
That's really the only way you can move it.
So I'm cool with that. That would explain moving that double bond to being there. Is that what you drew?
Would that mean I could add valence?
Is that what you drew?
So if you took away the double bond here, would that mean there would be that over there, and then a double bond would become
So I still want to go back to this. Is that what you drew? You're telling me this is what you're trying to do, and yet that's what you're drawing. Do these instructions match that drawing?
No.
You have to be aware of that.
But the only way you can move electrons is from the bond to the atom, right?
Or from bond to bond.
You can move it straight from bond to bond?
Yep.
I guess that's why I was like, oh, I'll just move it bond to bond.
Which is fine. You can go through and do that. But that's not the only thing you did. Right. Because you also have this.
Yeah, because I just moved it over there to do it.
And so if we were going to consider what happened, We had this nitrogen, you moved electrons towards it, and you moved electrons towards it. So you've got a scenario where you've got a center atom and you've moved all the electrons towards it. What are those electrons going to do when they see other electrons? Slow it down one step at a time. You should consider moving some away, yes. Okay. Is that an appropriate Lewis structure? And for the record, I drew it. So if that makes you go, yes, hold your horses. Just because I drew something does not mean I drew it right. So what do you think? Is that an appropriate Lewis structure? If your head shake means anything, I would say you're on the right path. That no, there's something wrong with that Lewis structure. So what do you think that something is? What do you not like about it? And where you circled was a perfectly valid place to circle. It turns out there's actually multiple things wrong with it. When we look at a Lewis structure, we need to be concerned that our atoms have octets. So they need to have 8 electrons around them. Do all of those atoms have 8 electrons around them? Okay, and this is where we run into a gray area. Yeah, they do, but they're implied. So it's going to become really hard to navigate this. If they're implied, you need to know what's implied and what's not. So a good first step might be to go through and make sure that there's nothing implied and you're aware of where everything is. Does that help make sense? Give that a shot. See if that helps. That was a good place to start too, where your pencil started to fall. Bless you. For the record, you were the very first person that I have seen do that. Yes. That is absolutely a good thing. It should have been step 1 from everybody.
I have a question about nitrogen. So nitrogen can only have 3 bonds, right?
No.
Okay. Because I was like, I thought. So then, what is the rule with that then?
A neutral nitrogen will have 3 bonds and a lone pair.
Mm-hmm.
There's nothing saying that that nitrogen has to be neutral. So if you're going to draw a resonance, you could very well draw a resonance structure where that nitrogen is not neutral.
Okay, so we could move the lone pair to as this as a double bond, and then this is a single bond, and then push that one up. Okay, and then I guess.
Now, is that a proper Lewis structure that you've drawn?
No, because this would need a negative.
Cool. Is that now a proper Lewis structure?
Maybe not.
Why maybe not?
Would the nitrogen have a positive formal charge?
Why?
Because it, well, I guess it lost the pair, but now it's a bond. So maybe, I don't think so.
So here, if we look at that pair, what is nitrogen sharing those electrons with?
The carbon that I just bonded.
Over here? What is that nitrogen sharing that lone pair with?
It's not.
It's not. It owns them both.
Right.
Here, does it own them both?
So that's why it would be positive. Okay. Okay.
So awesome. That's a good explanation behind it. That's perfectly valid to getting that to being the nitrogen being positive. So now, do you have a valid Lewis structure? Yeah.
Okay. So
Good
I
job.
think the bonding was, I was restricting myself with that because I was like, then I can't do anything.
Yep.
I was like, what the hell?
Which is a
Okay.
common issue that pops up.
Okay.
So I want to address a couple things that have come up just in walking around looking at everybody's table. We got 9 tables, so about a tenth of this class is doing a very good first step. The rest of the class, 90%, is actually missing a very important critical step. Okay? If we're going to talk about resonance, we're talking about what? Moving electrons. Okay? When we look at this drawing, are all the electrons visible? No. Okay? Back to our bond structures, we imply a hell of a lot of crap. Okay? Are you comfortable with that implication? I'm going to take silence to mean no. Okay? And I would kind of blanket statement say no, you're not comfortable. Okay? And I would argue I'm not comfortable with that. When I'm tasked with trying to draw out resonance, I'm not going to imply stuff. I'm actually going to draw those pieces on. So when we start this question, our first approach should be actually making sure that we've established where all of our electrons are located. Okay? And some of that has some extra implications. At least one person took it a step further. Okay? All of our atoms need octets. I look at the nitrogen and the oxygen, they're missing their octets, which means the first step I should do, add lone pairs. That nitrogen should have a pair, that oxygen should have 2 pairs. Okay? How do I know that? That's the common bonding patterns. That's why you need to have those memorized so that you can manipulate through these systems much quicker and more efficiently. Okay? So those electrons are present. Those are things that we could potentially move. Okay? At least one took it to the next level, which is perfectly acceptable, and I would argue it's a good move, particularly when dealing with some of the resonance structures that people are attempting to navigate. What else do we imply? Hydrogens. Okay? And I don't know that I necessarily saw it as I walked around here, but a very common resonance structure for students to go through and do would be to put the double bond here. Can I do that? Why not? Okay. If we're evaluating, there's a couple reasons that are going to get problematic with this anyway. Okay. If that was going to be our action, what do you think they did to be able to move the electrons to make that double bond? What did they move? They tried to move the double bond. They tried to say we took that double bond and we put it here. Okay. Curved arrows have lots of meaning. Those curved arrows are your explanation for how I'm going to navigate from one structure to the next. So for those people not showing curved arrows, you're making your life harder than it already is. Use the curved arrows. They're the explanation for the action you're taking. Okay? And if we use that curved arrow to help explain, I can't zoom in. And I now also show all my implied atoms. What happened to my carbon? It exceeded the octet. So that's a problem with this action. What else is a problem? The oxygen is actually missing its octet. Right? So if we're wanting to move that bond, that's okay to consider, but we need to consider ways that we can possibly move it, and we need to consider how to navigate that system. Kind of make sense? I should have explained what I wanted to first. Fuck. It's lost. So let's double back. God, let's double back. We're going to erase that structure. Okay, and if we're going to decide that we want to move that bond, okay, that pi bond, how can I move it? Okay, it's a bond. I'm allowed to move that from bond to atom, and I can also move it from bond to bond. Both of those are possible options. When you walk through the lecture video just goes bond to atom first so that you get used to those steps. And in the process of that, the very next thing we do is move from atom to bond. The net result is you could go bond to bond, but it's an immediate proximity kind of system. Okay? So some people will see that double bond and say, well, why couldn't I do this? Okay? Even if we ignore the fact that we have an octet issue here, let's say that that carbon was positively charged. Why couldn't I do that? Well, consider where the electrons are located. They're in a bond between what two atoms? Oxygen and carbon. Where are those electrons going to want to go? Why should they go to the oxygen? You mean those trends that we said at the very beginning of the semester are going to control almost every action we take? Yes. Yes, they will. Oxygen is more electronegative than carbon, which means, sure, I can move bond to bond, but does it make sense to take those electrons and move them to a bond away from the oxygen? That's a problem right away. So that arrow doesn't make physical sense, even if I could satisfy an octet there. I want that arrow, or my electrons, to move towards the oxygen. Okay? Once I have that arrow, I can now start to say, well, what does that mean? What does that result in? I remembered it. I'll come back to it. Maybe, assuming I don't forget again. Let's try and color code our actions here. Double bond, nitrogen, all of these in black because we did nothing to them, more or less. We even show that lone pair. There's that bond, oxygen. It had the two lone pairs to begin with. And now what did we do? We took that line, which represented, okay, two ends. You go with bond, and then you're going to get, which represents electrons, which represents how many? That's 2 electrons. That line represents 2 electrons. I'm going to say I'm going to move both those electrons to the oxygen. How do I know I'm moving both and not one? Nope. I can break that bond where I only take one. How do I know I want to take both? Look at the arrow itself. That arrow has 2 heads to it. Okay, you can break down language into different aspects and parts of it that hold meaning. That arrowhead itself is holding meaning. Because it has 2 arrowheads, I'm moving 2 electrons. If I only wanted to move one, I'd only use 1 arrowhead. This is something that is affecting people in smart work. Make sure you're using the correct arrows. Okay, so I want to move both, so I'm going to show them on that oxygen. Have I drawn a proper Lewis structure? No, why not? Formal charges. So once I've done my action, I now need to finalize and draw formal charges. How can I get to those formal charges? Did you memorize the bonding patterns? Awesome. You now know the formal charges are, since you said it, oxygen's -1 and fantastic, the carbon is positive. Okay, how else would you know? I don't think you guys were talking to me. How else do you know? Close. Is our drawing to start with correct? Yes. What was the charge on the oxygen? Okay, we'll come back to that. That's why we know we have negative and positive. That oxygen was what charge? Neutral. There was no charge associated with it. What does the arrow mean? It's gaining electrons. What charge are electrons? If I am 0 and I gain an electron, what happens? I'm negative. Do I need to have my bonding patterns memorized? No, I need to understand what the hell a curved arrow is. Do you? I don't know. That's part of this process. Okay? I would argue that's the method you want. Understand the curved arrows. Okay? How else could you do it? It's a painful way that I would argue a lot of you are at least using the language of in your approach. You calculate it. Any atom you've changed, you need to go through and calculate a formal charge. How do we calculate formal charge? Valence electrons minus the number of bonds minus the number of non-bonding electrons. Oxygen has 6 valence electrons, minus 1 minus 6 gets me a -1. I know the charge on that oxygen is negative. Okay, because Susan brought it up. Okay, if we got a negative, so cool, we've processed that, that's good. Is that a proper Lewis structure? No. How do we know? Why do I know it's got to be neutral? Because the original structure I started from is neutral. That's the only reason. If my original structure was negative, it had better damn well be negative at the end, because if it's not, I've somehow messed with my electrons. Okay? So if I found that negative and I recognize, whoops, it needs to have a positive in there, I now need to double back and try and figure out where that is. I could hopefully find out that there was only one modification I made, positive charge on that carbon. Make sense? Crap. I know everybody worked on this. Did anybody draw a resonance towards the upper left? Did you mean no? You mean no? Okay, cool. We're gonna make a modification. No, no, you didn't. Okay, we need to make a modification because we need to address the different aspects behind this. Yeah, a different aspect behind this that we'll see here in a second. Okay, so what we've now done is drawn a resonance structure. Okay, is this resonance structure better than what we started with? Absolutely not better than what we started with. What we started with, everything had octets, everything was neutral. What we ended with, why is that a bad structure? I don't know what stability is referencing. That's the proper answer. Not everything has an octet. I'm missing an octet, that makes that structure bad. It is also bad because I have charges, but that carbon is missing an octet. Okay? So to River's point, does that mean I don't want to look at this? No, I still want to acknowledge that that is a way that the electrons can move around. And that potentially exposes some chemistry that would allow me to chemically react this molecule further on down the food chain. Kind of, sort of? Okay. You want to try again? Draw some more? Yeah? Go for it. Is this you're drawing them on your own? Or are you talking to each other? Because it got real quiet. We got to get rid of the double bond for an example. Sorry, I apologize for that. I thought I could do it without getting rid of it, but no, I need to. Since you did it, I can go through and look at some of them.
Oh gosh.
Yeah. So yeah, this is cool.
This one, though.
Yeah, so that's awesome. I'm perfectly okay with that. Did you have to move it from this bond to that carbon? Or else could you have moved it?
To the other bond, but then you would have had. Well, I mean, yeah. Did I not do that? Oh, I guess I didn't do that. I thought that I did.
So if you did that,
But
because
that
it sounds like you already started.
For the nitrogen, though.
We're not talking about touching the nitrogen. All I'm doing is moving that pi bond to that carbon instead of to that carbon.
I thought you were talking about moving the pi bond here.
No, nope,
okay,
nope.
Okay. That makes more sense. Yeah, I can do that also.
Okay. What would that mean? What would your structure look like? Do you think you can do that in your head to talk through it, or do you need to draw it?
That would just make this a positive.
I'm dying a little inside when you do that, but that's okay. Generally, I don't want you to draw things on top of an instruction. So this would be like if I wrote my name where I wrote all the letters on top of each other. That's
Okay.
not clear. So if we were going to do it, you'd have to draw a new structure.
Oh, well, yeah, I
but yeah,
would,
okay,
but just
so-
for the sake of time.
So between this structure and this structure, which one is better?
I don't know, actually.
It's kind of a tough call. Okay, if we consider what this nitrogen can do, that's the one resonance you haven't drawn yet.
Yeah.
Okay? You have a lone pair of electrons on it that could donate out. They could donate out. If they donated out this way, what would they encounter? Oh, you did.
Yeah.
Okay. But you went towards the oxygen. If we went
Yeah.
this way, what would they encounter? A negative charge, right?
Okay. Yeah.
Is this a good resonance structure then? You're putting negative near negative.
No. All right.
Whereas here, you have negative near positive.
Okay.
Does that make sense?
Yeah.
Unfortunately, I think that is one I'm going to have to add the double bond back in. Let's say that again. You can. That is an action you can take. Is it a good action? Is it a valid action? I won't answer that. You should be able to answer that. And as you mentioned that, you gave me a solution. I can bring the double bond back. I can get the conversation I wanted to have. I can bring that back. That's diabetes. Jeez.
Able to move the lone pair and to make bond, right?
Yeah.
We can?
Yeah, you can.
Okay. Okay, so hear me out, guys. Okay, so can't you move this one here and then move that one there?
What atoms are there?
Carbon and hydrogen.
And how many hydrogens?
3.
3. You do this, how many hydrogens are there?
4. But
No,
there,
there's still
not
3,
but wait.
which would mean you've exceeded the octet.
Oh.
So can you move the double bond to that spot?
No.
No. And again, what you're doing is what we just walked through. You're taking the electrons from that double bond between the carbon and the oxygen, and you're moving them away from the oxygen. No, they need to go towards the oxygen. So can you get the double bond to that spot that you're trying to draw? No.
Can you make a triple bond?
You always can, whether or not your action is valid. That's where you're going back to interpret. Are you exceeding octets, any of that kind of stuff? For this particular question, I don't think you should be able to make a triple bond. I honestly don't know for sure, but I don't think you can.
Can you move this bond over here?
Try it.
I tried, but what about these lone pairs? Should I still draw the lone pairs or just consider?
Did you get rid of them? Can you just delete them? No, they're still there. Which means if they're still there, what's the problem?
Too many electrons?
So can you move that pi bond there?
I can, but it's not.
It results in an invalid structure, right? And if you have an invalid structure, you can't draw it. That's not an answer.
Okay.
Okay? So you could use the invalid structure to think about ways how you could undo that mistake to potentially find other options.
Okay, what if we move the nitrogen lone pairs that is on right here, made it a double bond?
Hot sauce.
It would exceed the octet.
Oh, no, it absolutely does.
Dude, this is so hard. I'm just guessing and checking.
Yes.
No.
Yes.
No, that's
You
not.
need to go through that process of guessing and checking. And one of the things you're going to encounter is the same thing I'm encountering with that up on the board is it's really small. Okay? When you shift those electrons in, you're trying to jam them into this tiny ass little space, which then means it's virtually impossible for you to see what to do and what to talk about. That makes it very hard to manipulate.
Because of this to that, isn't it? To this bond right here.
Yes.
And
What
then,
if we move these guys?
yeah,
Oh no, because that one's still there.
because the nitrogen would still have 3 bonds.
No, it wouldn't. It would have 4. There you go. I like it.
Or an octagon, whatever.
You better not be drawing octagons. There's no octets.
I'm just saying it's hard for me to draw hexagons for some reason.
I get that. You know, you're going to need some practice then. Or you can buy a little ruler thing that has the hexagons in it so you don't have to do it anymore.
This is the other one that we drew. This one is moving this double bond to the nitrogen.
Okay, cool. So let's pause. What happened to that lone pair? Are you saying it did anything or it just sat there?
It's a part of that. Then that would be too many electrons.
Answer my question first. Everybody's jumping to other questions. If you're going to move the pi bond to here,
Yeah.
did you do anything to the lone pair?
Oh.
Okay.
right?
Then if it is that bond, if that arrow represents how many electrons? 2, and you're saying this is also going there, how many bonds do you have there now?
Oh wait, no. We just did this one movement.
Okay,
Is that
and
what?
so now you've got problems because you're drawing an arrow saying the sigma bond goes there. No, it didn't.
Oh, I guess I just. So
Okay.
this was here, and I moved that to there.
Okay, so now you're running the system of saying, let me show you how to write my name.
Yeah. Okay.
Do you understand how to write my name?
So then, okay.
When you put it all on top of it, you can't tell what's going on, and you start to lose track of what was my initial state and what's my final state.
Yeah.
Instructions on a starting state,
Yeah.
draw the result
Okay.
every time.
Okay.
Do not draw on top because I don't know what you're saying was there before versus what wasn't.
Okay.
Does that make sense?
Yeah.
So to your original question of can you do this, I don't know because we still haven't gotten through what you're trying to actually do.
Right. Okay. Okay. But
So what we're going to do is take a look at another resonance structure here. I'm going to add a curved arrow. And we'll start it from our central one. So whoops, that was supposed to be an eraser. We'll get rid of that curved arrow because we don't care about that anymore. So here's a curved arrow. Draw the result. Yes, sir.
Okay. So when we're doing these runs right now, it's just there's only one bond. Is how we're doing it, or because you drew it back?
I drew it back up because I found a way to get to the question that I wanted to ask.
So was there a possible resonance up here?
There is once you have that double bond.
Okay, that's what because I thought I had something. Wait, I'm gonna draw it real quick just to see.
Yeah. And that's actually what I'm drawing up right now.
Okay. Because when it was double, you can move that one out, right? And then bring the one pair up here.
We'll talk about that action next. But yes. Okay, we're going to draw this one in red, full red, the whole structure for this single arrow. Okay, so we've got that red arrow. We're saying we're moving that electron, so all these other bonds don't change. So we're going to keep those all constant. We'll keep that lone pair on there, which, by the way, that lone pair is haunting a couple people, so you need to be careful with that. Okay, that arrow says I'm going to take that bond, that pi bond, and I'm going to put those electrons on that terminal carbon, which means that carbon has now gained a pair of electrons. That's what that means. Okay, last step. What's my last step? I've drawn a structure. Add the charges. So, how do I choose to do it? And by I mean you. How are you going to tell me where there's charges? Go ahead.
Can you explain what happens to the hydrogen?
So there's an awesome question. What happens to the hydrogens on your structure? Since we're talking about resonance, what bonds are we allowed to move? Or what electrons, sorry. Non-bonding electrons and pi bonds. How are the hydrogens connected to the structure? Sigma bonds. So what happens to the hydrogens? Absolutely nothing. Whatever was there in the first drawing is there in the second drawing, the third drawing, the fourth drawing. You cannot move them. So if we wanted to be more explicit and show those extra hydrogens, I know there were 2 hydrogens at that terminal position because I had a carbon that only showed 2 bonds at that end, which means I had to have 2 implied hydrogens, which means those 2 implied hydrogens are still here. And with those hydrogens now not implied, maybe that makes it easier to finalize our drawing. To finalize, what do we need? Formal charge. The only thing I've tweaked is where that double bond was located, which means the only atoms that are affected are the carbons that were connected to that double bond. One of those carbons now has a lone pair attached to it. And I could go through and calculate formal charge. Carbon has 4 valence electrons, minus 3 bonds, minus 2 non-bonding electrons, and that gets me a whopping -1 charge. Or I would acknowledge that my carbon started neutral. That arrow shows that electrons are moving towards it. It has gained electrons. If it's neutral and it gains a negative thing, it's going to become negative. Okay? That one we showed the hydrogens for. What happened to the other carbon? Okay? How do you know it became positive? Lots of answers can run with this. Okay? Go back to the curved arrow. It had access to those electrons. It no longer has access. I started neutral and I lost electrons. Okay? And if we lose things, of course we become... Wait, what? Why does it become positive if I've lost? Because what am I losing? I'm losing a negative charge. Okay? Negative signs will haunt you. They've probably already haunted you through 151 and 152. They're going to continue to haunt you through Gen Chem because what we're talking, or OChem, because we're talking about the movement of electrons. So you have to deal with what their charges mean. Okay? So you could do it based off of the arrow. How else could you do it? Structure is supposed to be neutral. If I know one of my carbons was negative, guess what? The other one's got to be positive. Process of elimination. Okay, I could also calculate formal charge. Formal charge is going to be real hard for that carbon because I've implied one of the bonds, that hydrogen. So I'd have to remember that I had that implied hydrogen there, or I would have to explicitly draw it in. Which of those many methods works for you? That's up to you to decide ultimately through practice. Okay? And again, where I will push you is to understanding of those arrows, because those arrows are going to run through the entire flippin' semester and next semester. You cannot escape them. Okay? So that generates this structure. Did I have to do that curved arrow? Okay, so a couple people said yes, so of course, what do we have to do? Prove them wrong. Couldn't I have done that? I could. What would the result look like? Okay, I don't want to show, can I not show those hydrogens, or do you want me to show them? People complained about my handwriting when I can zoom in. This is just getting worse. Okay. I'm glad you think it's lovely. I appreciate it when you tell me the truth, though. Okay. What happened? Those arrows showed the electrons went there. That meant that carbon now has a negative charge. The other carbon would be positively charged. What do you mean, does it matter? Elaborate. Okay. If I asked you to draw resonance structures, which of the resonance structures up here should you draw? Okay, which you may not have heard. There were a couple people that shouted it out for the recording. All of them. Okay. I said I saw 6 just as we started to do this out. I've picked up 2 or 3 more. Okay. Do you think, and yes, oh my God is an appropriate response. Okay. Do you think this would be a question that I would ask on a test? Well, we can tell where my opinion or where your all's opinion of me. No, no, no. Okay. This gets well beyond what this is trying to do is acknowledge where everything starts to manipulate out. Where this kind of a question has shown up in the past, okay, I've seen questions like this on the ACS test in second semester. Okay, and what they will go through and ask is where in this structure would you expect to see negative charge build? Tell me the atom numbers. So they would go through and they would number all the atoms and say, where do you expect a negative charge? Okay? So you're not being asked to draw resonance. You're being asked to interpret how electrons would move through an individual structure to each of those individual spots. Which gets us back to the red and the blue structure. Do we think they're both equally valid? No. Okay. Question of why or why not becomes a challenging one. So what we're going to do is we're going to put a pin in it, because I always wanted to say that. And we're going to say we're now done dealing with that pi bond that I said we shouldn't talk about anymore, and I deleted it and then realized that we could still talk about it, so I brought it back. And we're going to look at a different spot. Instead of moving a bond, because that's all we've done so far, I want to move my other option to move. What's my other option to move? Non-bonding pairs of electrons. Okay, so I'm going to take the electrons on my oxygen. Okay, I've got a non-bonding pair there. I'm going to color that one in green because I want to move that one. Okay, since it's on an atom, I can only move it to what? A bond. And why did I pick the oxygen? How many bonds are connected to it? That's fair to say too. How many atoms are connected to it? One, which means how many different locations can I move those electrons? Only one spot. Okay, so that simplifies things. So what I'm going to do is I'm going to move them to that one spot. Okay, and if you got alarm bells going off, that's a good sign. But of course, we're not going to listen to those alarm bells, and we're going to draw out the result. And by we, I mean you right now. You're doing a good job thinking. So hopefully you all have a drawing. Okay. Some of you might have even pushed all the way to charges, and I would say that's both a good thing and a bad thing. Actually, I'd flip that. I would call that a bad thing and a good thing. Okay. We'll talk. I will talk. We'll always talk. Okay. I redrew the structure. Okay. I ignored that lone pair for the moment because where am I going to move that? Into the space between the oxygen and the carbon. And if I have a pair of electrons between the oxygen and the carbon, I can turn that into a line. Now connecting them. That line is now a bond. So everybody should have this, and what I saw was pretty good for that. Then I saw people start to address charges. Why is that bad? You shouldn't do the work for charges. That's not a useful step. Why? Here's a big hint for why. That carbon has exceeded its octet. Because that carbon has exceeded the octet, this is an invalid structure. If it's an invalid structure, why bother to assign charges? This is not a structure I'm allowed to draw, okay, for an answer. Could I draw this as work? Absolutely. It's a fantastic structure to draw for work. Okay, so we will occasionally encounter issues where we have an invalid structure. We've exceeded the octet on an atom. How do we fix an exceeded octet? We need to move electrons away from that atom. What electrons are we allowed to move? Lone pairs and pi bonds. I'm super glad you said lone pairs first. Are lone pairs going to be useful to move? No. If your atom is exceeded its octet, when you move that lone pair, it still has access to it, because a lone pair can only go from an atom to a bond right next to it. So if you've exceeded the octet, there's only one thing you can do, and that's to move a pi bond. That pi bond must be moved away from the problem. My problem was an exceeded octet. So I'm going to look at my drawing and say, well, I need to move a pi bond away from the issue. I only have one spot for a pi bond that's right there. So I want to add an arrow to show those electrons move away from that exceeded octet. But I'm adding those instructions on something I'm not allowed to draw. That's not useful. Where do those instructions need to be drawn? On something I'm allowed to draw, which was the original structure. So what's my direction? I've got that green arrow. I'm going to turn the lone pair from the oxygen down into a bond. And what am I going to do? I'm going to take that bond and I'm going to turn it into a lone pair. What is the result of that action? The exact same drawing, which means not a useful action. That's all that means. Okay? And you're like, but I don't want to see wrong things. You absolutely 100% want to see wrong things. Because if I don't show you the wrong things, I know exactly where you're going to see the wrong things. You're going to draw the wrong things on the test and be like, well, I don't know why it's wrong. Yeah, because we never talked about the wrong things. You never thought through those questions of why this was wrong. You need to see the wrong things. Otherwise, you're flipping a coin each time. Okay, so that means those arrows weren't useful. So, what else could I do? Well, the whole point was talking about moving lone pairs. Can I move the lone pairs on the oxygen? No. There's no place for those to go. Those would be what's called localized to that oxygen. They cannot move around. Okay, do I have another lone pair? I do. Okay, I have another lone pair on the nitrogen, right? So let's go ahead and let's play with that one. We'll add another curved arrow. I'm going to move those electrons from the nitrogen to that bond. Draw the result. And if you're wondering, I intentionally left the green one up there, even though we're going to get another green one, but we're going to call that our yellow invalid structure.
Does this structure have like a ton of different ones? Because
The starting molecule, is there a ton of different ways to draw resin? Yeah, there's just a shit ton,
for
yeah.
this one,
Yeah.
Because
Like I said, I counted out 8 before we started, and I'm finding like 2 or 3 more.
okay, so like what's it called? So for this one, for example, like here, that would be one, but then also as a separate one, I moved these rings, but then another one would be that if it was like that and that. Okay.
Yeah, there's a ridiculous amount,
Okay.
yes.
That's what I thought.
Okay, for better or worse, I'm going to decide you're done and you've got it drawn. Everybody right? Cool. So we're going to start drawing it out. We'll draw the core structure first with no changes. Everybody at least mostly agree? Okay, where did I put that lone pair? In between where that nitrogen and carbon is, where it has a single bond, which means I need to now make it a double bond. Should I spend the time to evaluate charge? Okay, so we've got a couple answers. I've got a no because it's good. Thanks for the follow-up on that. I got a no. Why? Oh, interesting. We got no because it's a perfectly fine structure, and we got no because it's not good. Okay. How do we decide? Carbon exceeds the octet. What do you mean? I see 4 bonds. You remember that implied hydrogen? That implied hydrogen all the way at the very beginning, that carbon did not have a shown octet because there was an implied hydrogen. If I add that implied hydrogen to my drawing, what is now the problem? I exceed the octet. So this structure is bad, so I should not be dealing with formal charge yet because I have exceeded the octet. Does that mean this arrow is bad? Oh, and we got again mixed results. Okay? Same process that we just walked through. We moved the non-bonding pair into a bonding system, and then we have to evaluate our issue. Well, what's the issue? The issue is I've exceeded the octet. How is this new drawing different from this last drawing? We'll call this structure B, and we'll call this structure A. How is structure A different or unique than structure B? Too specific. You're 100% right, but too specific. How is structure A unique from structure B? You're rephrasing hers, which is awesome. Maybe we don't have an easy way of saying this. If we take a look at structure A and structure B at the invalid octet, when we invalidated the octet in B, what did we say we had to do? We had to fix it by doing what? Moving a pi bond. That pi bond has to be moved away from the issue. Okay. How is it different here? My issue is I've exceeded my octet. Why is this carbon special in comparison to this carbon? Why? There's a choice of pi bonds in structure A. In structure B, there was no choice. I only had one result, and that took me backwards. In structure A, there is the possibility to take me backwards. So yes, that is possible, but I also have an added possibility. I could do that. I could take the other pi bond and I could move it away from the issue. Am I allowed to add that curved arrow to this drawing? No, why not? I don't care why I need to do it. Why can I not do it to this drawing? Why does it have to go on the original drawing? This is an invalid drawing. I'm not allowed to draw this because I've exceeded the octet. Okay, so if I want to describe how to move my arrows, I have to draw valid structures each and every single time. So adding that blue curved arrow to structure A doesn't work because that's an invalid drawing. But what I can do is take that information, and I tried to zoom in again, and add the curved arrow to my top drawing. Because that was a valid drawing. What does that mean? That means I'm now using two curved arrows to explain how electrons are moving. I can do that? Yeah. How many curved arrows are you allowed to use? As many as you want, as long as you don't invalidate the octet with any of those individual moves. And what becomes the problem with adding more and more curved arrows? You increase the odds that you screw up that process and invalidate the octet in one of those steps, which is why I would say you should use as few arrows as possible as you're picking up skills with resonance. By the end of second semester, you should have internalized most of that, which is why the ACS can now ask a question about where's all the electrons moving, because you've internalized that resonance process enough that you don't have to draw out every flippin' structure and do all the little tiny arrows. Okay? So what's the resulting structure look like? Have you drawn it yet? I didn't ask you to, I was just asking. Did you? Yeah, some people have it. Okay, so 5 seconds. Draw it real fast. Five seconds was rude. It took me like 20 to draw it. Okay, and I still screwed it up. Right? There's a lone pair on that carbon. No. Yeah, go ahead. No. What's up?
What's the difference between invalidating the octet, like, and having the structure not be valid,
and then having one like that purple drawing on the bottom left, where we added a lone pair, but it still has 2 hydrogens. So isn't that octet exceeded? Because it has the 2 bonds and then
So-
2 hydrogens and then an additional lone pair.
So we got to be a little bit careful. The one with the lone pair
Yeah.
has 2 additional hydrogens.
It has, because wasn't that where the double bond went? Do you know what I'm talking
I'm gonna try and
about?
highlight.
Right
I don't know if
there, or
highlighting
is
worked.
that-
That looks that highlighted, right? That carbon.
Oh wait, I think I'm
Where's that carbon?
Okay. I think I just got mixed up with all the single and double bond.
Where you got mixed up is I went through and I deleted that double bond.
Yeah.
That's where you got mixed up. That's my
Alright.
fault.
All good.
But you're on board?
Yeah.
Is there an undo? There's an undo. Cool, that worked. Okay. Do we now have a final structure and we're now, yay, happy, everything's grand? No, of course not. What's wrong with my drawing? Formal charge. I've drawn the structure, I've got my electrons, but I have to make sure I address all my formal charge. As I go through to address the formal charge, hopefully what we'll note is that that is a fat marker. Dude, because it's highlighting? That looks better. Negative there, and then nitrogen will be positive. Okay? And if you're struggling with that, that's okay. Go back and reference that, but that's how that structure comes out. Okay? So what I really wanted to push to is you can try and draw resonance structures, and you'll draw things that are invalid. It is okay to have an invalid structure. Realize we can fix invalid structures. We fix them by adding another curved arrow. That's our work process. So one of the things that I used in the tutoring center is if we were going to do the math of 19 plus 30, no, I'm already skipping ahead. I have to pick numbers that I can do math with. Plus, let's do 14. What's the answer? Cool, 33. Okay, but if I go through and do this, or actually my kid does it better than me already. Okay, if I ask my son to go through and do it, he's going to get 33. And I'd be like, well, where's your work? Well, I didn't need work. I just did it in my head. Okay, that's cool. Well, I get it. Okay, but what's the work? 9 plus 4 is 13. I didn't write 13. I wrote 33 because what did I do? We wrote the 3 and carried the 1. Now 1 plus 1 plus 1 is 3, and there's my 33. Is this 1 my answer? That's not my answer is 33. What is that 1? That's my work. That's the process I'm using to simplify this. That's the point of these invalid drawings. These invalid drawings are painful because it's not just a little 1. It's this giant, nasty, gross-looking structure. Okay, but that's your work. Okay, that's the work part of this. That's what you're using to help you think through and reason through each of these steps. Kind of, sort of? So, okay to hit invalid structures. Think through ways that you can fix the issue at that point. This is why I'm circling the issue. The issue is that exceeded octet. I can only touch the electrons around that spot. Okay? Which then takes me back to the red and the blue structure. Entirely different note. Which of those two structures is more appropriate, the red one or the blue one? Talk at your tables. We've already heard a couple answers. Fight it out at your tables first, and then we'll fight it out as a class.
They both have. The red one is.
And negative. They're right.
It's switched, so
Isn't that the same thing? They're just switched. The formal charges and the lone pairs.
Yeah. Yeah. So,
they're the
So
same.
neither one is better because they're the same.
okay, that's fine. You're wrong.
Because it's got 4 bonds. It went.
So you think we have an idea yet? Or as we started the fight, we were like, oh, it's the red, it's the blue. And then somebody else came up with and said, aren't they both the same? So there's technically 3 different answers that you could use. There's actually a 4th. No, there's not a 4th. That's a lie. Okay, 3 different answers, red, blue, or both. Which one's the best? Everybody's ready? Oh, a question? Okay, I won't.
Which I was actually going to ask before you did the group.
Okay, fair.
But are either of them even, like, could we even call them valid resonance structures because the positive charged carbons don't have their octet?
So they are valid, and so this is what she was talking about too. Okay, they are valid because they haven't invalidated their octet. They're under octet. Are you allowed to be under octet? Yes. Is that a good thing? No. So if I was asked to rank stability between red, blue, and green, green is going to be the best because every atom has its octet. The original, now multicolored fiasco in the middle is going to be the absolute best. Every atom has its octet and no charges. Kind of, sort of? Okay. So blue and red are valid resonance structures. They do help us to understand where the electrons are located. They are technically bad resonance structures. And now what we're pushing on is one even worse than the others. Is that a hint?
Red is worse than blue because red has a positive carbon with a nitrogen with a lone pair, so they can interact with each other. So I would choose the 2 negative closer to each other.
Okay, so your argument is phenomenal, just backwards. Okay, so because I don't think that went through in the recording, and people over here may not have been able to hear. Her argument was looking at the red structure. She was saying is the worst, okay, of red versus blue because you have that positive next to that nitrogen with the electrons, and those could interact with each other, right? Okay. For that very reason, which of these is the best? The red structure. Okay. Because I can cancel that missing octet. How do I cancel that missing octet? By moving the electrons from the nitrogen. That gets me that green structure. Okay? If we look at the blue structure, the only way to cancel that octet is by reverting backwards, having the lone pair come back in. There's no ulterior path to stabilizing that missing octet. The red structure is going to be better because I have multiple ways to stabilize that octet. Okay, which is going to introduce some interesting potential things that we could consider within this. Okay, what happens when I bring electrons near electrons? They repel. What does the nitrogen have? What is that lone pair? What happens when I bring electrons near electrons? They repel. Oh, that's a higher energy state. Yet if we look at the red one, what happened? I have electrons near not electrons, which means the electrons can actually kind of cancel out and interact more favorably. Kind of, sort of? Okay. We are looking at a very advanced molecule here because what we're trying to do is think through all our possible resonances. Eventually what happens is we look at a molecule like this and we say, what are all the possible things that can react? Well, that nitrogen has electrons. Because that nitrogen has electrons, it could donate those electrons with something else. Okay? That carbon, that terminal carbon, has electrons, which means that carbon can react with something else. Okay? The carbon where the oxygen is, attached to 2 electronegative elements, that makes that carbon very positive, which means that positive can now react by accepting electrons from something else. So what we're trying to do is find the imbalances of electrons within our molecules so that we can start to guess what are we going to react it with. That what we react it with is now later in the semester and all of second semester. You're trying to understand how those electrons can distribute so that you can make reactions happen. And resonance is a key player in all of that. So for instance, we didn't talk about that bottom part, Could we talk about that bottom ring? Yeah. Okay. There's largely a reason why we didn't talk about it, and well, actually, it's because I forgot about it, if I'm going to be perfectly honest. Okay. And I probably didn't need to draw it. But I could go through, we'll go on the green structure, that's an eraser. I could take that pi bond and I could move it to that bond. That would exceed the octet at the next carbon, which I decided to highlight in green. Okay, so I could move the next pi bond, to the next bond, which exceeds the octet at the next carbon. So I could move the next bond over to the next bond. And you'd be like, well, isn't that going to exceed the octet there? We already moved the electrons away, so it doesn't exceed the octet. So what's the result of using those three arrows? I've done resonance. I've moved the pi electrons around the ring, and not only have I moved the electrons, did I create any missed octets? Did I create any formal charge? No. What does that suggest about the electrons in that ring? Yes, perfectly acceptable. What is that going to mean about its reactivity? Not very reactive. And what we'll find is that that ring structure, particularly if you study just OChem 1, doesn't react. If you move into OChem 2, we can always make something react. You can worry about that in OChem 2. But right now, ring structures don't react. Okay? If you're looking at those electrons, we can constantly move them around the ring. We have an internal resonance system that makes them very, very stable, and we don't have to stress about it. Kind of, sort of? Do we feel better about resonance? That was a big transition. Yeah? Okay. You are not expected to be perfect with resonance yet. Okay? Like I said, it's going to come up in second semester again. You're supposed to be getting towards that track where you're understanding where those things move and how they move so that you can start to make these larger predictions. It is something you should be constantly practicing, but realize the majority or the rest of Unit 1 is now looking at how we draw things and we represent those structures. Okay? So we get resonance as this big nasty beast, and then we kind of take a step back and be like, it's just an art class. How hard can it be? If you've never taken art, it can be really hard. Okay? So the rest of our content is mostly how do we draw these structures? Messily. Okay? Which sets up another potential issue. Was this really clear looking at those red arrows? Were you able to see all that? Okay, so some people, like up here, it was too bad. Caleb in the back is like, dude, you need to take some art classes. Okay? That's really small. And yet when I go through to look at your work, guess how big your work is? Your work is even smaller than what I'm drawing on the board. You're having a hard time seeing this, and if we consider the size of that drawing, right? Stop drawing small. Why are you drawing small? Because I want to conserve paper. I'm sorry, it's not an ethically conscious class. Okay? Draw big, draw messy, get it on the paper so that you can start to evaluate it and see what you're working with. Okay? Questions? Yes? That's cool. I'm sure we would love a break.
The electrons in the oxygen are localized, and would the lone pairs on the nitrogen also be delocalized?
Okay, so cool. Good discussion back to it, because localized and delocalized is kind of hand in hand with resonance. Okay, so the oxygen lone pairs, we said we couldn't do any resonance with. They're localized to the oxygen, they can't move. How about the electrons on the nitrogen? Are they localized to the nitrogen? No, we could move them into other bonds. So the nitrogen lone pairs are not localized. What's not localized? Delocalized. Okay, so yes, that's an important reference.
Would the lone pairs move away from the electronegativity?
Which is a good question. So if we look at that green arrow, because I think that's the best representation for that. If we talked about how we moved electrons, where did we have to move electrons? Yes, towards an atom or a bond, but typically towards the electronegative, which is why when we looked at the oxygen, the yellow arrows for our oxygen, we said those were trash because we're moving the electrons away from the electronegative element. What are we doing with this green arrow? We're moving them away. But Mike, you said that's not fair. You can't do that. In the case of the yellow arrows, you're moving them from the bond, not just away, you're removing them from the oxygen. Oxygen has lost all access by doing that action. Is that the same thing that's happening with the nitrogen? No. Okay, which sets up a different question. The nitrogen was the lone pair. I see a lone pair in my resulting resonance structure on this carbon. Are those electrons the same? Okay, that's a really weird gray area, but I would argue no. Okay, the lone pair did not jump from the nitrogen over to that carbon. The lone pair from the nitrogen went to make a pi bond. That pi bond caused an imbalance that caused the electrons in the next pi bond to move out to the carbon. Okay, so when we're moving those electrons kind of away from the nitrogen, that away is still accessible by the atom. Yes. Okay, hugging to holding hands versus the dingo ate my baby. Right? No? Okay. It's made sense in my head. Oh, shit. Old reference. Thanks. Okay, fine. You feel better about it at least?
Yes.
I guess if you got it, that makes, yeah, there, okay. We good? Okay. What do you want to look at? Or are you saying you're just done? I got 2 minutes. You mean the thing that I just deleted everything from? I don't know that I have an undo button that's going to go that far back. The best one was the initial drawing. Oh yeah, look at that. Was the initial drawing. So the next best after that is going to be this green one. So, and realize we didn't show all the resonance structures. Okay, we barely skimmed the surface of our possible resonance structures. But our best between black, red, blue, and green is going to be the green. Why is the green better than the red and the blue? And actually, for that matter, the black. Poor little word. We're looking for octets. Okay. The green one has all of our octets satisfied. Okay. This green one, we moved that nitrogen lone pair up to the left. Did we have to move it up to the left? We could have moved it to the right. And if we moved it to the right, we'd be seeing the double bond appear on the right-hand side. Would that have resulted in a valid resonance structure? Depending on what you're seeing, yes or no. But yes, ultimately you could move them to the right. Could you move those electrons down to that ring? Yes. Yes. Okay. So the question of what's best of that set becomes really challenging because we've drawn maybe 1/10 of our possible resonance structures. Good question. Okay, which might have used up my 2 minutes. I think it did. Can someone send me an email about the worksheets? Because I keep forgetting to link them. So I would argue these are rather extensive. I'm looking at them, I'm like, I can't believe I thought people would be able to complete this in a lecture period. Like maybe one box makes sense, but like there's a crap ton of questions within each of those. So I can try and get those uploaded so you've got some more potential practice behind those. After that, we are there, so we'll go ahead and end on time. I don't like doing that, but it's probably appropriate.